Welcome to another unit of the ISM exercise set Business Mathematics. This time with a unit on derivatives. Let's take a look at the exercise. Here we have calculate the first derivative of function f and the first and second derivative of the function g. Here that's f, that's x divided by y times exponential function of z, and the function g is x squared times sinus of y minus z. Okay, let's take it one at a time. We start with the first one. And if we take a look here, we see, well, the derivative for x, that's pretty straightforward. That's just the x is only above the fraction line, so we could also pull this in front or behind the fraction. Then we would directly get our derivative. However, for the derivative in regards to y, and in particular to z, we would need to have an additional part to be done, and that's using the quotient rule, because there we need to work with this as a rational function. So we just note this here. However, the first derivative is for x, so here, as I said, I can just pull this in front or behind the fraction. Then it's just 1 divided by y times exponential function of z, because the derivative of x would be 1. So this part is easy. However, for the second part, as I said, we need the quotient rule. So first off, if we want to calculate this here, we take a look, what's our g? Our g here is x, and x derived for y is 0. Then we have the function below the fraction line, the denominator function, that's our h. So here it's y times exponential function of z. Well, if we derive this, we just left with exponential function of z. And yet then we can just use these 4 different functions to plug them together in the quotient rule and get our derivative for f in regards to y. So we would have here 0 times h, this would be 0, minus g times derivative of h, so minus x times exponential function of z, divided by h squared, so y times exponential function of z to the power of 2. This would look as here. Thereby, we have the second of our 3 partial derivatives. We only need the one for z. However, for the part with z, we have the same function, the same quotient rule, and we work in the same fashion. Because again, our g here is x, and the derivative for z is 0. Our h is again the part below the fraction line. So here in this case, it's y times exponential function of z. The y can be treated in this context like a constant, because there's no z inside. So here the derivative is just, again, the same thing as before, y times exponential function of z. If we combine these 4 functions, we get derivative of g, so 0 times h, 0. So minus g times derivative of h, so minus x times y times exponential function of z. All of this divided by z, by y times exponential function of z, parentheses to the power of 2, making it look as this part here. With one addition, this looks slightly different than what I just mentioned, only due to the fact that I already shortened out one of the exponential function of z. So it makes this a bit easier. This is something which I also had done with the y part. Okay, and then I have my derivative for x, for y, and for z. and I can summarize them, and they look as follows. As you see here, in the derivative of y and z, I just shortened out one exponential function of that. This makes this a bit more comparable to the first one. Okay, this then is the solution for the first of the two functions, the derivative of the first of the two functions. Let's now turn to the second. With the second, here with our g, this is however way easier, because here the variables are clearly, well, different in different places. You don't need any quotient rule, product rule, chain rule. We could just start with the derivative for x. So it's just the x squared. The minus, the times sinus y does not matter because in the sinus there's no x. So this is treated like a constant. And the minus z is omitted because the derivative of minus z in regards to x is 0. So here we have just 2x times sinus y. That's the derivative for x. Then, regarding y, we only need to consider the sinus y. Derivative here is cosinus y. And again, cosinus y times x squared, because the x squared in this context is treated like a constant. Again, the minus z derived becomes 0. And taken together, we only have x squared times cosinus of y. Then finally, we have the derivative for z. The full first term does not contain any z's, so the derivative of the full first term is 0. And we only have minus z to derive, and the derivative of minus z with regards to z is minus 1. So if we summarize this, looks as follows: 2x times sinus y with regards to x, x squared cosinus y with regards to y, and minus 1 with regards to z. Okay, and still remains relatively simple if we now derive this again for x, y, and z. If we go with x, we only have 2 sinus y. Then we have 2x cosinus y and 0, because minus 1 derived for x is 0. So this is 2 sinus y, 2x cosinus y, 0. Then we go for y. Here the 2x remain as a constant, and it's 2x times cosinus y. Then we have x squared times derivative of the cosinus is minus sinus, so we have minus x squared sinus y, and then 0. And then finally for z, well, there's no z in any of the three of them, so it's 0, 0, 0 as derivatives. Making my second derivative look as follows. So the Hesse matrix here, that's as given as follows. And I know that I'm not so wrong with these results, because we know the Hesse matrix for any normal functions is a symmetric matrix, and well, this matrix here is symmetrical. So this is a good indicator that we actually calculated correctly. Well, this then already concludes also this the second and last part of this exercise. And I hope that you enjoyed listening to it. And if you're looking for more of these types of exercises, feel free to visit the rest of this exercise set or the corresponding playlist. I say goodbye and see you next time.